But what does an inerter actually do? In the last few weeks, I received this question hundreds of times, since when my recent video went viral and collected about 1 million views. What is surprising is that that video was a 50 minutes long conversation between two academics, myself and Professor Malcolm Smith from the University of Cambridge. And that's the last thing that you would expect to go viral. Of course, there were compelling elements to the story. We were talking about Formula One and how Professor Smith invented a new mechanical device called the Inerter, how McLaren developed in secret the Inerter, used it, and how then this device was involved with the spy scandal of 2007, which is the biggest spy scandal in the history of the sport. Despite the positive comments and support that I received for that video, many viewers were left puzzled or confused. Even engineers or people with an engineer background didn't fully understand what an inerter does and actually misunderstood it. But the thing is this. Many people misunderstand the inerter, and this has been the case since the beginning. In fact, the engineers at Renault that had a drawing of the inerter taken from McLaren didn't understand the device. And that's why Renault, despite committing industrial espionage, was not fined. There is even a conspiracy theory in Poland which says that the inerter is a stolen invention, that it was invented before by a Polish engineer. And again, this conspiracy theory is completely based on a misunderstanding of what an inerter does. People think that it's something else. In fact, there is no resource online that is both accessible and fully correct that explains what an inerter does. There are some popular videos that touch on the topic that give some compelling explanation, but they actually miss the point. So why is it so easy to misunderstand the inerter? And what an inerter actually does? With this video, I want to fix that. I want to answer these questions. I want to create a resource that is both accessible and completely correct. To achieve this objective, I will employ the following strategy. I will explain the inerter 3 times, every time at a higher level of complexity. I will start with something that is called the LE5 on Reddit, which means explain it like I'm 5. So I will use a simple analogy to give some intuition behind the important elements of what makes an inerter unique. In the second level, I will use Formula One language. So I will assume that you are a Formula One fan, but without any engineering background. Finally, in the third level, I will give the full engineering explanation. But I will do so without assuming that you have an engineering background. I will exploit the previous levels and the intuition that we have built using those levels to make you understand and see what an inerter is. I will use this video also to explain common misconceptions. Why the inerter is not a damper, is not any kind of damping device, and why that conspiracy theory that I mentioned has no foundation. As a bonus, at the end of the video, I will also include some clips from the original interview with Professor Smith, which I did not include in the original video, because some of them were too complex, and essentially it was not possible to follow them without the proper background. Let me know in the comments below if you were able to follow all 3 levels of explanation, or if I failed and I lost you before, and let me know where I lost you, and I will be happy to try to reply to your questions. So let's dive in. The first level is the LE5, explain it like I'm 5. Here what I want to focus on is to explain what is called system thinking. Before doing so, let's watch a short clip from the original interview. People misunderstood how this was working. So in one way, the idea is very simple, but in the other way, it escaped so many people. So why do you think this is the case?
Yes, I think that it's partly to do with electrical engineering thinking versus mechanical engineering thinking, systems thinking versus a more reductionist way of thinking about a mechanical system.
So Professor Smith referred to system thinking as the right way of thinking about inerters. Let's try to explain this with a simple analogy. Imagine that you own a restaurant, and every weekend there is a special customer that comes and they have a very long list of food that they would like to eat. Your objective is to prepare a menu that covers as much as possible the wishes of this customer. In this analogy, the restaurant is like the Formula One team. The customer is the racetrack that changes every week. The racetrack has features like bumps and curbs that will cause oscillations to your car. Your objective is to design a suspension system for the specific road features given by the specific racetrack. However, there is a problem. Your restaurant only has forks and knives. This limits what you can cook. You can only make food that can be eaten with forks and knives. In our analogy, forks are like springs and knives are like dampers. That means that when designing a suspension system, you are limited to just these two devices. Then here arrives a professor that says that they invented a new device called a spoon. Thanks to a spoon, you can eat liquids, but most importantly, the professor says that it completes the trilogy of cutlery. The chef is perplexed by this explanation. They start to think about how to use the spoon. They think that you can use the spoon to eat porridge, for instance. The professor replies, sure, you can use the spoon to eat porridge, but that's not the point. So the chef thinks more, and they say, okay, maybe you can use it also for soup. And the professor say, yeah, sure, you can do that, but that's not the point. And the chef say, okay, maybe for yogurt. Sure, you can use it for soup, porridge, yogurt, but that's not the point. So what is the point, says the chef? Well, the point is that the spoon completes the trilogy of cutlery. What matters is that thanks to spoon, knives, and forks, you can consume any food.
Systems thinking versus a more reductionist way of thinking about a mechanical system. The latter, where you want to ask, what does this element do on its own? Whereas the systems way is you're asking what is happening to the whole system, the closed looping control systems terms, or the vehicle together with the suspension system and all the components working together. And it's the richness of the component set that one thinks about in terms of the availability, widening the available behavior.
The real value of the Inerter is not just in what it does on its own. Sure, like a spoon lets you eat soup, the Inerter enables some new behavior. But the real value of the Inerter is that it completes the trilogy of elements. It unlocks the full design space of suspension systems, like having forks, knives and spoons lets a restaurant serve any dish. I want to stress here that when I say the full design space, I mean it. It means that any possible passive suspension system, and these are an infinite number, they can be designed thanks to just these three elements. So let me now reply to some common questions that I received. The first question is the Inerter a kind of damper? No, not at all. First of all, the Inerter is a new kind of device. Like a spoon, it's a new kind of cutlery with respect to a knife and a fork. Sure, like a knife and a fork, a spoon is used for eating. And similarly, an Inerter, like a damper and a spring, are used in a suspension system, but they serve different purposes. Why so many people think that an Inerter is like a damper? First of all is because originally McLaren called the Inerter J-damper. They did that to confuse people, to hide the real device. But this confusion persists. People still think of the Inerter as a kind of damper. The other reason why we think that the Inerter is a kind of damper is because whenever we are introduced with something new, we always try to understand that thing, that new thing, by making analogies with what we know already. And so when someone comes with the Inerter, we think, okay, maybe it's like a damper. But actually, if we really want to compare the Inerter to something that we know, the Inerter actually is much more similar to a spring than a damper. That's the case for spoon and forks. Spoon and forks take food from the plate, they store the food and they carry it to the mouth and then they release it at the right moment. That is exactly the same behavior of springs and Inerter. They are energy storage device. At a certain point, they collect energy, they store it, and then they release it back into the system. That's fundamentally different from a knife or a damper. Dampers dissipate energy. They convert that energy into heat, and that is lost. It's dissipated away from the system. An Inerter does not dissipate any energy. An Inerter is a lossless device, like a spring. That means that an Inerter is nothing like a damper, like I will show you later at the engineering level explanation. Question 2. Is the Inerter a kind of tuned mass damper? Again, no. A tuned mass damper is a secondary system that mixes masses, dampers and spring to help to control oscillations. If you want, you can imagine this as a combination of a fork, a spoon and a knife joined together, but very heavy. This device weighs 10 kilograms, and you can imagine that it's very large, so it's not very comfortable to eat food. It's not a spoon, a knife and a fork. It's an approximation. It helps, but it doesn't work very well. It has many drawbacks. The third question is the Inerter a stolen Polish invention? Again, no. There is a narrative in Poland claiming that the Inerter is essentially the same as a device invented earlier by a Polish engineer called the EPAR, which is short for Energy Accumulating and Dissipating Converter. However, the EPAR is, as the name suggests, an energy dissipator, much like a damper, or in our analogy, a knife. At the second level of explanation, I will actually show you the patent of the EPAR, where this is made clear. So while the Polish media engaged with the idea of a stolen invention, the international scientific and engineering community regards the Inerter and the EPAR as distinct devices. Now that we have built some intuition, let's move on to the next level of explanation, aimed at curious Formula One fans with no engineering background. When a Formula One team prepares for a race, one of the most critical tasks is to tune the suspension to match the current track's characteristics. Think curbs in Monaco, high-speed corners in Silverstone, or bumpy braking zones in Montreal. The objective is to reduce oscillations on the car. The reason is that if, for instance, after a corner the car oscillates and the tire is not properly gripping the ground, then the car cannot impose the maximum force to the ground and accelerate as quickly as it would. To achieve oscillation reduction, engineers rely on springs and dampers. A spring stores energy when it's stretched and compressed. In other words, when there is a change in relative position. It then pushes back with a force that tries to return things to their normal position. In a car suspension, hitting a bump compresses the spring, which then releases that stored energy to help the wheel settle back down. It should be understood that an ideal spring is a lossless device. It returns to the wheel exactly the same amount of energy it received. A damper resists movement when its ends slide towards or away from each other. In other words, when there is relative velocity. A damper dissipates energy by turning the movement's energy into heat. In a car suspension, it stops the spring from bouncing the wheel up and down for too long, so that the ride quickly becomes smooth again. Now, Formula One teams only had these two tools, springs and dampers. With them, they could control how the suspension behaved, but only to a certain extent. Certain vibration modes, ride frequencies, and transient responses were difficult to control. Then along comes Professor Malcolm Smith, and he introduces a new mechanical element, the inerter. So what does an inerter do? Let's first explain it like a chef explains that a spoon is just for eating soup. An inerter is a mechanical device that behaves a bit like a mass, but not in the usual sense. It creates a force proportional to the relative acceleration between its two terminals. Let's try to visualize what two-terminal means. The inerter is added to the suspension system, like in this graphical representation of the Renault front suspension system, which I'm showing here for educational purposes. This representation is just a possible configuration, but it clearly shows one characteristic that makes the inerter unique, which is its two-terminal nature. You can clearly see here how the inerter joins together two almost symmetrical parts of the suspension system, each with its own damper. The two connections point of the inerter to the two parts of the suspension are what we refer to as terminals. Then it is clear that the two parts of the suspension can move independently of one another, and the inerter will exert a force which is proportional to their relative acceleration, which means proportional to the difference between the acceleration of each part. In simpler terms, the inerter reacts to suspension movements by resisting how that movement accelerates. While this is similar to what a mass does, differently from a mass, the force created is proportional to relative instead of absolute acceleration. This means that a mass, differently from an inerter, would exert a force that is proportional to the acceleration of the mass itself, not of the relative acceleration between two terminals. To know why this difference matters and thus why an inerter allows us to do something that a mass cannot, we need to wait for the third level of explanation because this difference requires higher precision in our language. For now, we move on. In Formula One language, the result is that now you can fine-tune how the car reacts to certain specific oscillations, like a mass will do, but without adding an actual mass. However, this explanation that I just gave you is like our chef telling you that spoons are just to eat soup. It is a possible use of the inerter, and it is a correct explanation, but it is ultimately a limited understanding of its value. The real value of the inerter isn't just what it does, but it's what it unlocks. The inerter gives engineers a third degree of freedom when tuning the suspension response. The value of the inerter is that it completes the true trilogy of mechanical components. Just like in the previous level we talked about forks, knives, and spoons, here it's about having a complete toolkit to shape the dynamic response of the car exactly how you want it. In fact, as I will explain later in the third level of explanation, the inerter unlocks the design of what can be considered the perfect suspension system. Now let's go back to the three questions. Question 1. Isn't the inerter just a type of damper? No. Dampers dissipate energy. That's their main role, to convert motion into heat and settle the car. The inerter, on the other hand, does not dissipate any energy. It stores it in a different form, kinetic energy related to acceleration, and then it gives back this energy into the suspension system without any loss. In this way, the inerter is much closer in spirit to a spring than to a damper. Both springs and inerters store and release energy without any loss. Question 2. Is the inerter just a type of tuned mass damper? Again, no. A tuned mass damper is a secondary system, usually a heavy mass on its own spring damper setup that's tuned to counteract vibrations at a specific frequency. It's a brute force way to cancel oscillations by letting one mass, the one of the mass damper, fight the other, the mass of the car. Tuned mass dampers are effective, but they come with a cost, added mass, which has other unwanted impacts on the car. One of such impacts is that the tuned mass damper oscillates independently of the oscillation of the suspension system. It is, to use technical jargon, a movable aerodynamic device. This specific property was ruled illegal in Formula 1, and the tuned mass damper was banned. An inerter, however, gives you better vibration control, and it does not add real mass. The constant of proportionality of an inerter, called inertance, can be arbitrarily large, while the weight of the device is kept unchanged. Thus, an inerter that weighs 1 kg could have an inertance of 200 kg or 300 kg, for instance. Why was the inerter not banned like the tuned mass damper? Because if we have, for instance, a spring connected in parallel with an inerter, then the two terminals of the inerter do not move independently of the suspension system like the mass damper did. In technical jargon, this means that an inerter is not a movable aerodynamic device, and consequently, it does not violate F1 regulations. In short, you can think of a tuned mass damper as an approximation and a heavy device. Inerters, on the other hand, are light and precise devices. Question 3. What about the polished device, EPAR? Is that the same thing? No. The EPAR, which is short for Energy Accumulating and Dissipating Converter, as the name suggests, dissipates energy. That makes it a damping device, not a pure energy storage device like the inerter. People have been misled into believing this conspiracy based on the incorrect understanding that an inerter dissipates energy, which it does not. Why do people believe the theory in the first place? Because some embodiments of the inerter look similar to the EPAR in the sense that both inerters and EPAR have flywheels, but plenty of mechanical devices have flywheels. For instance, look at this push and spin kid toy here. This toy is often used to illustrate how an inerter works. Unfortunately, this comparison with the kid's spinning top contributes to create confusion about inerters. By exerting a force on the lever, the energy is stored in the flywheel. But answer this question, where does that energy go? Do you see it going back into the arm of the person pushing? No, that energy is dissipated away. This toy lacks the fundamental property of the inerter of giving back the energy without losses. An inerter does not dissipate energy. The point is that the release of the energy back into the system is just as important as the storage, and it is what contributes to make the inerter unique. In contrast, the EPAR is very much like the push and spin toy. It dissipates energy. In fact, this device is a car bumper. It was developed as a way of improving car bumpers when a car crashes into another. It is a clear energy dissipator. Its primary goal is to absorb and get rid of the energy from the impact, much like a shock absorber. All these differences are not minor, they are fundamental. In mechanical systems, whether a device stores or dissipates energy leads to very different dynamic behaviors. In summary, the narrative of a stolen invention has no ground in either the technical facts or the legal history. The devices have different functions, and the direct legal challenge to the Inerter patent was unsuccessful. Now that we have built this middle-level understanding, let's move on to the engineering-level explanation, where I will demonstrate to you what an Inerter really does and why it changed the game. To explain this properly, and assuming that you have no background, I will start with the basics. We consider an oscillation represented by what is called a sinusoid, which is a curve like this. A sinusoidal signal is described by three key quantities: amplitude, which is the distance between 0 and the peak of the curve; frequency, which is the number of peaks per second; and phase, which is the horizontal shift of the wave compared to a reference starting at 0. Now let's consider a simple suspension system made of a spring, a damper, and an inerter. I represented this with a simple schematic here, where this symbol represents a bump velocity source. You can think of this source as the effect of the wheel going over a road fissure, generating a sinusoidal velocity input. We now want to understand how the suspension affects this input. So we go to the output side of the suspension, which is connected to the car, and we measure its oscillation. This is what we get. For comparison, the black curve is the input oscillation, while the blue curve is the output oscillation. We can observe that after an initial transient behavior, the oscillation settles into a periodic curve. The early part, where things are still settling, is called the transient behavior. What comes after, where the oscillation repeats in a regular pattern, is called the steady-state behavior. For our analysis, we will ignore the transient and focus only on the steady state. Now, here is the question. Is there a pattern that tells us how the oscillation changed from the input to the output? In other words, is there a way to predict what the output of the suspension system will be given a certain road fissure? They look quite different and it's not easy to find a similarity. So let's try with a different example to see if we can notice some kind of pattern. We try with a different suspension configuration, like this one here. However, we use the same sinusoidal input. Now let's measure the output. It has clearly changed, but in what way? At first, the change may seem unpredictable, but there is one thing that never changes in any of these results. Can you spot it? It's the frequency. Every output oscillation has exactly the same frequency as the input. This is a fundamental property of what in jargon is called a linear system. We will not define what a linear system is, as this is off topic, but the key fact is that this property is possessed by any suspension system made of springs, dampers, and inerters, no matter how complex. In fact, regardless of where you measure, at the car body or between components, the steady-state signals will always be sinusoidal of the same frequency as the input. This observation is at the heart of many techniques in engineering. If a system always produces output oscillations of the same frequency as the input, then to fully understand the system, we only need to study how much the amplitude changes, this is called the gain, and how much the phase changes, this is called the phase shift. How can we study this? Here is an idea. We input a sinusoid at 1 peak per second. We measure the output gain and the phase shift, and we record them on two plots. The first plot is gain versus frequency. The second plot is phase shift versus frequency. Then we change the input frequency to 2 peaks per second. We measure again and plot those values. We repeat this process for many frequencies, and we eventually obtain a plot like this. This is called a Bode plot. The top plot shows the gain, that is how much the amplitude changes across frequencies, while the bottom plot shows the phase shift across those same frequencies. This Bode plot tells you everything about how your suspension system responds to any sinusoidal road fissure at any frequency. Let's look at another example. This particular Bode plot shows that at a frequency of 5 peaks per second, the suspension reduces oscillation's amplitude by this gain amount. That means that this suspension system is effectively filtering out bumps at 5 peaks per second. Now you can see how powerful this tool is. If you know the Bode plot, you know exactly how your suspension will behave for any kind of sinusoidal road input. So let's flip the question now. Let's say that you are a Formula 1 team and you need to design a suspension for the next race. You use data from telemetry of the racetrack and models of the car and suspension to perform simulations of the complex interaction between the road, the suspension, and the car, to try and determine the best possible suspension system. By doing so, you find that the best lap time will be obtained by a Bode plot like this. We will not discuss here how such a design process could be carried out. What matters is that a suspension with this Bode plot produces the best lap time in simulations. But now that I have a nice Bode plot, what am I supposed to do with it? The question now becomes, if I have a desired Bode plot, can I actually build a suspension system that matches it? This is where Professor Smith comes in. Professor Smith knew that in electrical circuits, as long as the Bode plot stays within certain limits, specifically as long as the phase shift stays between minus 90 degrees and plus 90 degrees, then it is always possible to build a circuit that has exactly that Bode plot using just resistors, inductors, and capacitors. Thanks to the current force analogy, which we explained in the previous video, he expected that the same should hold for mechanical systems using springs, dampers, and the mechanical equivalent of capacitors. Up to that point, it was believed that the mechanical equivalent of a capacitor was the mass. But Professor Smith realized that a mass is not the mechanical equivalent of a two-terminal capacitor. The mass is only equivalent to a capacitor connected to ground. So for instance, you could convert this electrical circuit into a suspension system because the capacitor here is connected to ground, but you could not do the same for this circuit because there was not a mechanical equivalent of this specific capacitor not connected to ground. That meant that the design space was incomplete. Without the missing element, it was impossible to build certain suspension systems, no matter how many springs and dampers you had. This is why the perfect suspension system, one tailored exactly to your Bode plot, was physically impossible to realize. There was a gap between the maths and the engineering. Professor Smith eventually found a solution. He invented a new mechanical element, the inerter, specifically to complete the design space, exactly like a spoon completes the set of 3 basic cutlery together with forks and knives. The story of how he came up with the invention, including how the inerter impacted Formula 1, is covered in detail in my original video. If you haven't watched it yet, I recommend doing so. So going back to some of the questions, is an inerter a kind of damper? Let's try to see what happens when we connect a bump generator to a single damper, a single spring, and a single inerter. This is what we get. For the damper, we see that the input and output oscillations have the same phase, meaning that the peaks happen at the same time. Because the phase is maintained between input and output, if we compute the energy dissipated, we can see that the energy dissipated keeps increasing, like shown in this plot in blue. Now we do the same for a spring. What do we notice? We see that the output sinusoid is shifted with respect to the input sinusoid. In particular, this shift is by 90 degrees, and so we say that the output lags by 90 degrees. Now we compute the energy dynamics of the spring, and we plot it in green on the same figure as the one of the damper, for comparison. We obtain the following plot. We see that the spring accumulates and releases energy periodically. In doing so, it never dissipates it. Now we do the same experiment for an inerter. The behavior is symmetric with respect to that of a spring. The inerter's output has a phase shift in the other direction. So this time we said that the output leads by 90 degrees. Similarly, we can compute the energy dynamics for an inerter, and we see in red that this is similar to that of a spring. It accumulates and releases energy periodically. There is no dissipation. So to go back to the question, is an inerter a kind of damper? You can clearly see that it is not. A damper dissipates energy. Instead, the inerter, like a spring, stores and releases energy without dissipation. There is a popular video on a channel called Donut, where they give an explanation of what an inerter does. The video is very nice, and to be a non-academic channel, the explanation is quite good and compelling. It is not my intention to go and nitpick on other people's videos, especially since I really enjoyed that. But certain statements in that video are incorrect and contribute to the confusion around inerters. Let me start with what is good in the video. First, the video correctly explains that an inerter does not dissipate energy. It is laudable that the video explains this correctly. Second, the video gives an intuitive explanation of what an inerter does in a very special situation. When an inerter and a spring, both tuned to the resonance frequency, are connected in parallel, They oscillate against each other. The result is what is called a distractive interference, namely the two oscillations tend to cancel each other. However, the video also has some errors. First, the video states, and I quote, that to get rid of high amplitude oscillations, you need a big flywheel, which has a lot of mass. This is incorrect. The inertance of an inerter is controlled by the pitch of the screw thread. For instance, an inertance of 200 kilograms can be easily realized with a flywheel weighing just 0.1 kilograms. Second, the video refers to the inerter as a damper, which is incorrect. The logic of the video is that since in their parallel connection example, the inerter cancels the oscillation of the spring via disruptive interference, this can be interpreted as dampening the oscillation. However, by the same logic, one could call the spring a damper, as it does exactly the same, namely, it dampens the oscillation of the inerter. Calling the inerter a damper is incorrect, and more generally, the term damper should be reserved to dissipating devices. The third issue is that the example used, although intuitive, is very special. If you change anything in their example, then the intuition they gave breaks down. For instance, if the spring and the inerter are connected in series instead of then in parallel, then nothing of what the video says about disruptive interference is correct. Their explanation is the equivalent of the chef claiming that a spoon is just to eat yogurt. Any reductionist explanation like this misses the real value of the inerter, which is to unlock the construction of a suspension system which perfectly matches a desired body plot. Whether the resulting suspension system has an inerter in parallel or series, or why that inerter is there and what is its role, does not matter. What matters is that that magic configuration of components realizes the desired body plot. As promised, I want to end the video by showing you a couple of clips that I had removed from the original interview with Professor Smith because they were a bit too complex or a bit off topic. Let's watch this one. So what you're saying is that you know that given any circuit, you have a method to build a circuit, so you know how to arrange the components to realize that theoretical circuit. And you want to use the same idea for mechanical synthesis. Is that correct?
That's correct. So there's a theory that goes back to the 1930s where engineers characterized the circuit, all possible impedances that you can realize. So the simplest case is a one-port, a two-terminal device. So you have a box with electrical components in and two wires coming out. And the voltage current relationship across those terminals is the impedance or the complex impedance. And a very beautiful result was derived back in those times to characterize exactly what class of complex impedances would be realized, and that you could build such an impedance with resistors, capacitors, and inductors. So that was the theory that I thought should be applicable, because we had a characterization now of this black box, an electrical black box. So let's do the same for a mechanical black box. Right. And that replaces with your powered hydraulics and your spring and damper. You have a mechanical black box, which is going to be the suspension system. And it satisfies this condition on the complex impedance, which we know from the electrical domain. It's something called a positive real function. If you do a frequency response, then the real part of that has to be non-negative for all frequencies.
The sketch that
in fact, this is a sketch of it. So that the red region is the forbidden region. So the complex impedance has to remain in the right half plane. So another way of saying it is that the phase difference between current and voltage has not got to exceed 90 degrees. It can go up to plus 90 or minus 90. But any frequency variation between zero frequency and infinite frequency that respects that the phase shift never becomes more than 90, is that that characterizes a positive real function. It's actually easy to see that that's a necessary condition for a complex impedance to be passive. And it's a simple, you take a sinusoidal current and a sinusoidal voltage and you integrate over a cycle. And you use your trig formulae to show that if the phase shift is greater than 90 degrees, actually the power that you're integrating over a cycle becomes negative. So over one cycle, you can pull power out of the device. So it can't be passive if that phase shift.
If you get energy out of it, yeah.
Yes. So the more difficult part is to say, given any curve that behaves that way, and you have a box of components, can you build a circuit to realize that curve? And that's the theory, the electrical theory. By the way, just a brief aside, there are two analogies here, and the one you've described is the newer one. The older one is the force voltage.
So
mapping force onto voltage and velocity onto current. And that has its origins in the 19th century. People would use the term electromotive force because they thought voltage being like force. But the advantage of the one we've described, that's based on through and across variables, is that series connections in one domain become series connections and the other parallel become parallel. So the circuits are topologically identical. A vibration mount, and you have a vibration at a certain frequency that you want to eliminate. You could use that idea of an inerter in parallel with the spring to provide a mechanical notch filter. And that contrasts with a classical way of solving that same problem. The tuned mass damper is used for vibration suppression, a mass on a spring, very much the same idea that Renault used in their suspension.
So I hope that this video has helped clarify what an inverter actually does, why it's an important and unique device, why it's not just another kind of damper, nor something that had already been invented before, and why explaining what an inverter does is difficult and so many people misunderstand it. Let me know in the comments if you have been able to follow all three levels of explanation, or if I lost you along the way. Either way, I'm glad that you watched. See you next time.